My name is Dan Nussbaum from the Naval Postgraduate School in wonderful Monterey, California. Thank you for coming to this track. Many thanks to Lynn Wells and the TIDES program, for George Mason University for sponsoring this year, and for the team who will be on this energy track of Kristen Fletcher, Bill Anderson, Kevin Maher, and Brandon Naylor. I'm going to tell you a bit about the Naval Postgraduate School and the work we do in the Energy Academic Group. So if we can share the screen, please. Standing by.
Okay, you don't see it yet, huh?
No, do you?
Let's see. I do. So here we go.
Oh, good. Thank you very much. So as you see on the first screen, my name, the department I'm in, but I also chair something called the Energy Academic Group, more about that later, and a picture of the iconic Herman Hall, the old Del Monte Hotel in sunny and cloudy, sometimes Monterey, California. Next slide, please. You have to have an agenda, and I do. A very short background on who we are, both at the school and the Energy Academic Group, and some of the things we do, and how this fits into a much larger context. Next slide, please. So a very short thing about who we are. We are America's National Security Research University. We're in beautiful Monterey, California. We have many graduates. We have many students from around the world. We have about 1,800 students who are in residence, not quite now, of course. About double that in distance learning. We have about 20% international students. The students come from all services, Army, Navy, Air Force, Marines, and Coast Guard. Very few civilians. You actually get sent here. I think what you need to know is that we are a fully fledged, completely accredited university tucked inside the U.S. Department of Navy and in a beautiful location. Next slide, please. The Energy Academic Group was established 8 years ago, and you can see the mission. The mission is really to pull together the disparate threads of energy across the campus and even in a larger context. We decided that we have 3 pillars, which you can see highlighted there. I'll talk about each one, but they're what you'd expect from us in a university: education, research, and outreach. We have really an interdisciplinary group that reaches out in many directions. I'll talk about education and research and outreach in the subsequent slides. Next slide, please. We are cross-functional, and you can see some of the threads that we try to weave together, because when you think about energy, there are sort of 2 threads. There's the operational energy that powers your ships and aircraft and so on, and there's the installation energy, which runs your bases and camps and installations. So we need to thread together operations research and logistics and supply chains and all those kinds of things. From the educational perspective, we run master's degree programs and we run certificate and short courses. Some of those short courses are completely open to the public. You'll hear about that in the last representation by Kevin Maher, so stay tuned for that. We are also putting together new courses, as you can see on this slide. But we really have a robust education part of what we do. Next slide, please. I do want to say that if you had to walk away now and wanted to know what did Nussbaum say, this is what Nussbaum said, that energy is important. My subtext here is you already know this, and if you don't agree with it, I hope to hear from you that you don't. But energy is important, and it's complicated. It's a high visibility issue, and it's not going away. But there are people who look at this, and there's help available if you want to talk about it. In the bottom banner, I say that these are issues that you should think about in your own contexts. They're both local and global, national context and international contexts. I have a particular interest in the NATO arena and the European Union arena, as well as the US national security arena. But the key takeaways on energy are what's listed on this slide. This is big, this is important, it's visible, and it's not going away. Next slide, please. I want to go back to education. We've done some short courses overseas. We have not done anything, of course, recently in the time of COVID, but you can see the kinds of things we've done. When you look at critical energy infrastructure protection, you'll hear more about that from Professor Dan Eisenberg later on in this track. We have a defense energy symposium where people come in, do a video, and then we curate those presentations on a website. You can see that in the middle of this slide. We also have some new things in the works, but particularly I draw your attention to that website where you can see some very, very interesting topics. Next slide, please. So education is one pillar, and I've talked to you about master's degree, some certificate classes, and the Defense Energy Seminar. Now I want to switch to research. I just want to give you a flavor of some of the research, and there's a great deal that's going on, and I'll highlight one at the very top. Suppose you wanted to go from point A to point B, and you had to be there in a certain time T. Now, this could be for ships or aircraft or your car or anything, but in our context, it was ships. It's got to get from here to there, and it has to be there by a certain time. You can set the power controls for fast or slow, or a little bit fast and a little bit slow, but all of that has energy implications. And since ships, by and large, run on fossil fuel, you'd like to use less fossil fuel rather than more. If you don't like fossil fuel, you certainly want to use less. And if you like using it, you want to save money and have more fuel in your tank when you get where you're supposed to be to do your job. So we have a number of nice tools, one of which is called Otter, and you're going to hear from Brandon Naylor later about those kinds of tools. So I put on here some of the research that we've done, just so you can take a look at it. Happy to talk about that further. The next slide, please. I want to shift to a larger picture. So if you ask how much energy is used, where does it come from, and where does it go, I've got this sort of chart. This is always the beginning of analysis. Where does it come from? Where does it go? So the arrows are from and to. The thickness of the arrows is how big it is. You know, so the black arrow from coal to power generation says, hey, that's a pretty big number. By the way, over time, the thickness of that has shrunk and gas has gotten bigger. So this is an important thing. It's a bit outdated, but it's roughly right. And if you want to save on energy, you have to look for the big arrows. So at the bottom, the green one, which has oil going to transportation, well, there's an opportunity there, isn't there, in electric vehicles or hybrid vehicles. So that's an important background slide. Next slide, please. A bit more analysis would show that energy comes from various places and it's going to various places over time. What you see here, as you read from left to right, is that total energy is going up. You'll see later on maybe that actually it's not the Western developed economies that are going up so much, but it's the developing world. But when you look at that left-hand slide, or the right-hand one, you could come to the bottom banner, which I put up there in a provocative way, which is, it looks like hydrocarbons are not going away. More or less, hydrocarbons forever. You may not like it, but that's what the data suggest. Now, the IEA has just come out with some new numbers, so the shape and slopes of these curves are a bit different from what I have here. But you know, I still think that bottom line is roughly right. And I think that is a real topic of conversation. You can see where I got that data from the website that is towards the bottom of the chart. Go to the next slide, please. What you can see here is that energy comes from a variety of places. The top half of this was what was going on in the year 2000. The bottom half is the year 2040, projected, of course. And what you have here is where the demand came from. The demand really has changed, right? It used to be that the US was the big demander, and China was not, and now it's reversed. You'll see that the US doesn't have less demand really than in 40 than in 00, but we're no longer the big demander. The growth in demand, the growth that is behind the banner that says hydrocarbons forever, is coming from elsewhere. And so that's important. It's not going away. Let me look at this a bit differently on the next slide, please. You've got Russia's role in European energy, all right? So in each of these, you've got 2017 and then first part of 2018. And what you see is that Russia supplies an expanding percentage of people's energy needs. Is that good or bad or indifferent? Well, energy security, broadly defined, means not being beholden to somebody. It also means for the supplier not being beholden to a given buyer. So behind this chart are arguments like Nord Stream 2 and energy out of the Caucasus and the ability to diversify both suppliers and demanders. So if you're in NATO or in the European Union, this slide gets to be a topic of conversation. Next slide, please. People love to talk about energy security. So I put up a slide on energy security just for sort of a standard. That second dash is 4 A's. Available, so the energy can be found. Accessible, meaning you can reach it. Affordable, you can see it, reach it, and get it at a reasonable price that people will pay. And acceptable, by which I mean sustainable and suits sustainability standards. So that's a definition of energy security. Is that the only one? No, but it's one. Move on to the next slide, please. I want to talk about one kind of energy that's of very great interest to the Department of International Security, and that's operational energy. The stuff that drives ships and aircraft and vehicles and bases and stuff and things that are used in security arenas. So why is operational energy needed? Well, for the obvious reasons, strategic, operational, and tactical, you see that. You see the pie chart that a FOB, a forward operating base, how does it use its energy? It uses it mainly for environmental control units and water purification. So if you're into the expeditionary business of national security, Marines, for example, you get to worry about where am I going to get my energy to run, well, what do you need? Where does it come from? So operational energies needs are important. If I need to spell out further why it's important, take a look at the next slide. And you see some reasons here why it's important, reasons that you know. And this brings us into the region of supply chains. Supply chains can be quite fragile, as you know. And so you have to worry about how we're going to move the energy from here to there, and how much do we need? So how much do we need would be under the last bullet. If you look at, okay, hold on a second, sorry. If you look at that last bullet, recent new weapon systems like Littoral Combat Ship or F-35, which has been in the news, these are more energy intensive than the legacy systems they replaced. So you have the sort of the oddity that we need more and we have to push it across fragile supply chains. Go to the next one, please. Next slide. So security of supply, you can see that there's a problem, whether we're pushing things across oceans or on aircraft carriers, and we get to worry about the cost of things. So this is not an exhaustive list of the things that represent danger to the supply chains for this critical element of energy in the national security business. So now I want to put on my operations research and cost estimating hat and turn to the next slide and say to you that if you start with a gallon of fuel here and you want to get it to the fleet or forward operating base, how much fuel do you need? How much are you going to use up in that transportation? And the answer is about half. You want to get 100 gallons somewhere, you better start with 200 gallons. Because you can see from left to right how energy gets from here to there. That's sort of a simplified view of the chain. If you look at the next slide, we have losses associated as you move from step to step. So roughly 2 to 1. Roughly 2 to 1 is what it costs. So if you can save a gallon where you need it at the end point, you're actually saving almost 2 gallons up front. What could go wrong in these supply chains? I'm on my last 3 or 4 slides. So here's a short list of what could go wrong. These are places where you spend a lot of energy and things can go bad. And if you want a real specific example, take a look at the next slide. The Straits of Hormuz, like the Straits of Malacca, are very narrow sea lanes through which great deals of energy move. In this case, it's the source of energy. In the Straits of Malacca, between Singapore and Indonesia, you have the place where China's energy comes through. Without it, China lacks about 10 million barrels a day. So there really are risks to supply. I want to end by doing the thing that all academics do, which is what kind of research areas are available on the next slide. And there are some questions that are ripe for research. Right? Choosing options, developing costs. What is a pound of energy security cost? What are the right ways to spend capital expenditures to optimally create energy security? Standard kinds of questions, but very hard questions. If one is new to this business, and you say, hey, Nussbaum, what should I read to get me started? The next 2 slides are 4 books that you will enjoy and will bring you much farther along than you are if you're starting now. So take a look at the next slide and the next slide. Good, thank you. So you'll take a look at those. So let me conclude on that note. Thank you for your attention. I hope that wasn't too fast. I'm always available for questions. And I'll now pass this to the next speaker, whom I will introduce in a minute. Thank you. Can you turn that off?
Just a second.
Our next speaker is Bill Anderson. Bill is the Director of Utilities Engineering Management Division at NAVFAC, that's the Naval Facilities Engineering Command, at EXWC, that's the Expeditionary Warfighting Command, at Port Hueneme, California. And they deliver energy security through microgrid solutions globally to include remote island sites such as San Nicolas Island, Diego Garcia, and McMurdo in Antarctica. Bill's PhD research provides a resilience assessment framework for islanded renewable energy microgrids, generating the resilience and costs trade space for design exploration. Bill was formerly a management consultant and previously a career Civil Engineer Corps naval officer. Bill?
Good afternoon. Thank you for giving me the chance to speak, and I'm looking forward to this time to share with you what I've been privileged to have the opportunity to do, and that's research further for my PhD, a method for us to assess resilience and in turn be able to measure it in a way that allows us to show the design trade space that influences resilience and cost. And quite simply, what I'm trying to do, what I hopefully you'll present and show you that I can do, is put a price tag on resilience so that decision makers, base commanders, can figure out what is the more optimal combination of resilience and costs as a result of different design changes in microgrids. So let me just jump right in. I'm going to start by saying in this methodology, this framework that I've developed, I'm defining resilience to be the microgrid's invulnerability and rapid and full recoverability from an improbable and severe disturbance. So I know that's a mouthful, and what I'm going to do is I'm going to show you how I view that. So what you're seeing now is a microgrid resilience curve, and this is rather traditional, but it shows on this curve performance as measured on the y-axis, in my case microgrid performance, over time on the x-axis. And as I've defined resilience, I'm looking at when you see this curve first drop, that's when the disturbance hits. The key cornerstone of resilience is it's in response to a disturbance. So this disturbance causes degradation, the performance drops, the microgrid stabilizes, and then it recovers. And what I'm measuring are two measures that I've come up with. One is invulnerability, which is over here, the top to bottom, which measures the immediate drop in performance. And then I'm measuring recovery, which is the time it takes for the microgrid to recover, return to its earlier pre-disturbance level of performance. So those two measures, invulnerability and recovery, directly tie to that definition that I presented. And as I mentioned earlier, they are tied to, different than reliability, they're tied to a disturbance that is, and my definition, I said improbable and severe, but typically we talk about it in terms of HILP, high impact, low probability. I emphasize that because that's the differentiator in what I'm doing, what I propose resilience does, in that it's looking at a high impact, low probability disturbance vice a low impact, high probability disturbance that reliability assesses. So this is the lens, if you will, that I am looking at assessing resilience, okay, using those two key measures, invulnerability and recovery. So I'm using those measures, I've developed those mathematically to measure for a microgrid. And to do that, I built a model, and this is, I'm showing you a quick screenshot of my resilience model in Excel. And why I'm showing you this is so you can get a sense that this tool will take inputs to this model, which have to do with the DER, the distributed energy resources, how many, what is the capacity, what type, how many wind turbines, how many solar photovoltaic panels, how many diesel gensets, how many batteries, what capacity they are, power capacity, and then you choose the disturbance. In this case, I've chosen hurricane. You just choose your maintenance level that you're investing in. In this case, I've chosen medium, and then you hit run, and the model will calculate resilience on those two metrics I mentioned, invulnerability and recovery, but more importantly, tying back to what I'm showing you now, is a cost model where for those choices in design, you enter in different cost parameters. You enter in the economic life of the wind turbines. You entered in your weighted average cost of capital. You have to earn your planning horizon, and any distinct assumptions that you might have for the location as it relates to the CapEx, the capital cost, the maintenance costs. You put that all in, and then you hit run, and then the model will generate these scores for invulnerability, recovery, and a aggregate those two to get a resilience score. That is the essence of the model based on what I shared from the microgrid resilience curve based on the definition. Now, what's valuable about this that I wanted to share with you is we can now explore the design space so we can better understand which choices in design and maintenance influence resilience and cost. So one easy basic way that I'm going to show you to do that is what we did at St. Nicholas Island, San Clemente Island, and Gitmo. And I'm showing you now, if you look at this graph here, you're seeing, it's a three-dimensional graph, you're seeing 3 different color curves. Red is San Clemente Island, purple is San Nicolas Island, and green is Guantanamo Bay. So we use the model and basically allows you to see that if I have 3 diesel gensets and I come into, let's say 2 wind turbines right here, I see that at my green curve, which is Guantanamo Bay, for that combination of 3 and 2, I would come up to the curve in here, and I would see my resilience at about 0.675 on the curve there. Similarly, then I see at San Clemente Island, I have more resilience for that same combination. But interestingly, I see a big step here, which all that tells us is that at Guantanamo Bay, going from 2 diesel gensets to 3, I see a much greater improvement in resilience than I did at San Clemente Island. So obviously there's some other takeaways, and there's a similar graph to this where we graphed the same choices against cost. So you can flip between the two. Now that can be a bit tedious, but still useful. Now, the more powerful feature of this tool and what we are proposing for decision makers is to actually, let's look at different either ratios or redundancy levels to see how they influence the resilience and cost. So right here on this graph, I'm showing you a 4-dimensional graph. And the 3 dimensions are the power capacity ratio here, the cost here, the resilience here. And what this is telling us is I've plotted based on my model in the 4th dimension is the maintenance level. So if you see the maintenance levels vary, whether it's none, low, or medium. But this allows us to see and allows us to view in the screen, you see me rotating, a little bit of a stall in Zoom, but allows me to rotate this view and home in on points that are indicative of decisions that I would want to make. So this tells us, as I look at this curve, that my costs go down as the power capacity ratio goes up. And this is the ratio of renewable energy power to combined microgrid power, considering a hybrid microgrid. So that's an interesting point here. It's telling me that I really want to be at a sweet spot here of 0.67 where my costs start to go down, but I have to be careful on any trade-off curve because at that point over here, I'm seeing my resilience starts to drop off as well. So it allows us to make design recommendations that are more likely to give more resilience for the amount of cost that we're willing to assume for that decision. And then the maintenance levels are interesting here too. The darker you see are telling us that that's no maintenance. The lighter in the dots is more. And then the shape has a lighter color overall as my resilience increases. So it allows you to decide, okay, how much maintenance is right? What is the right ratio of power capacity? And the last slide I want to show you is we looked at this from redundancy levels for different architectures. And this shows you here that I've got redundancy levels from no redundancy of all the way to a redundancy level of a quintuplet, that being out here. And what this is allowing us to see is effectively, as redundancy increases, my resilience increase, but interestingly enough, my cost decrease, okay? And that's an important point and distinction that we could glean from this, and very useful. But other pieces that we can take away from this is, if I look at these gray shapes, this is a shape of a microgrid that had wind turbines, PV, and DG. And it's telling us in that shape, where you see the darker one beneath the gray one, that maintenance, which is no maintenance of dark, matters much more in that combination than it does the other curves, where the maintenance level has little variation impact on the resilience or cost, but it has much more here in this architecture, the gray one. So again, in this one, like the last one, we can rotate through this, we can change our perspective. This is through the lens of redundancy perspective. But now if I want to shift and look at it from a cost perspective, I can do this. And you can see I get some other interesting knowledge that allows me to better recommend where we want to be in terms of that redundancy level. But the real kind of big takeaway is more redundancy provides more resilience for less cost. And similarly, back to this, the power capacity ratio, we can see, you know, as we look at for this architecture, that there's a optimal point that I want to not exceed in terms of my power capacity ratio, so that I ensure that I'm not overspending for the same incremental improvement resilience. Unless I want to, of course I can, but I have to be careful here. If I do too much, I lose in resilience. So that's kind of the overview of what we can do with this model. Again, the big value, and we're implementing this at Rhoda. We are working on it at McMurdo for National Science Foundation, is it will allow us to better explore that design space so that we can provide a decision maker their ability to choose an optimal point of resilience versus cost. And that's the extent of my model, unless there's further questions.
I would unshare the content. Good, thank you, Bill. That's just terrific, and I really do appreciate your presenting it. If people want to get in touch with Bill, you want to just tell us what your email is?
Absolutely. So I'm at Bill, B-I-L-L .Anderson, A-N-D-E-R-S-O-N, the number 1 at Navy.mil. That's M-I-L.
Great. Thank you, Bill. I appreciate that very much. And we'll move on to our next speaker. All right. So good. Our next speaker is Brandon Naylor, who joined the Energy Academic Group at the Naval Postgraduate School in 2017 as a faculty associate in research. Brandon's educational background is mechanical engineering and robotics, and his current research focuses on microgrids, modeling, and optimization. His noteworthy projects include an experimental containerized microgrid lab at NPS and something called the Otter Surface Ship Fuel Optimization Program. I think we'll have a chance to hear about Otter. Brandon graduated with honors in mechanical engineering and a minor in robotics from Rose-Hulman Institute of Technology. He's earned a Defense Energy Certificate at the Naval Postgraduate School, and he's pursuing a master's in mechanical engineering at NPS. Brandon, thank you very much for being here. Over to you.
Thank you for that introduction. Kristen, can you pull up my slides, please? Great, thank you. So today I'll be talking about containerized microgrids using commercial off-the-shelf technology and microgrids intended for ad hoc systems, resilience at installations, and other situations where you might not want to develop a full microgrid for your entire base, but perhaps microgrids for maybe a single facility on your base. So when we talk about microgrids, size is definitely one of the big constraints. How much do you have to spend? What are the benefits of different architectures? So we'll go into why are we doing containerized systems? Slide. So the benefits of using containerized systems are that the standard ISO shipping containers that are used to move freight around the world are extremely affordable, readily available, and highly mobile. They're easy to load onto a truck. You can store them in a warehouse. They're easy to prepare at one facility, move somewhere else, and just have them, at the ready whenever you need to establish an ad hoc network. For example, if in the Virgin Islands or Puerto Rico when the hurricane hit, if you had a big warehouse full of these, it would have been easy to mobilize them in a hurry. The other benefit of having a containerized system is that it simplifies the operation and logistics end chain for the end user. A user doesn't have to source all the individual parts. They just pick up or request a microgrid from these depots that would be pre-established if one were to pursue this type of strategy. They don't have to figure out what type of inverter they need to use. They don't have to figure out what type of battery storage they need to use. They don't have to customize the solar or wind generation for their individual environment. Someone else has already done all of that work on the front end, packed it up into a box, shipped it to them, and now they have a scalable one-size-fits-most solution. And when I say scalable, I mean take multiple of these microgrid boxes and daisy chain them together until you have a grid that's big enough to meet your needs. The additional benefit of having these systems containerized in a box is that these boxes are weather tight. They're designed to protect whatever is being shipped across the ocean, so they'll be more than suitable for protecting the equipment inside on land. And this is a particularly noteworthy aspect of them because one of the main applications for these types of microgrids would be in disaster environments where the weather might not have cleared up yet. You might still have some residual storms, and you're dealing with equipment that might be sensitive to moisture. So the commercial off-the-shelf technology has come a long way, but it's not quite as hardened as the military technology, which is why having these weather-tight containers is important. An additional benefit of having a containerized in-the-box solution is that having these things pre-made drastically reduces the training requirements that's needed by operators in order to get these systems up and running. You effectively have a box that you just plug and play. You can hook it up to the breaker box of a building you want to power, or you can establish these at your tent city or whatever it is that you're establishing at your disaster relief station, and you're good to go. You don't have to have people who are specially trained in how to size a battery or how to size a generator system. Next slide, please. So the additional aspect that I'm working on is exploring the benefits and viabilities of commercial off-the-shelf components. So one of the main benefits of commercial off-the-shelf technology versus things that have been purpose-built for military use is that we benefit from an existing infrastructure that's already in place to serve the civilian, industrial, and commercial markets. Because these are being sold to a wide variety of customers, we benefit from a low-cost quantity of scale. We also have a diverse network of established suppliers that already have their supply chains in place, so we don't have to worry about what if one supplier needs to get their hands on materials that have no longer become available in a certain area. If that supplier loses access to a material, then we have lots of other suppliers we can go to. We also have technical support network that's already been established through the technical support that's required to service their commercial, residential, and industrial customers. We don't have to establish new manuals, new training materials, any of that. The other benefit of commercial off-the-shelf technology is that it's all designed to work with other commercial off-the-shelf technology instead of purpose-built equipment where it's expecting a certain type of hookup. Most of these systems are agnostic as to what type of battery you're using, or they're able to adjust between 4 or 5 different battery types. They're able to accommodate different types of solar setup in terms of what type of voltage is coming in or how much amps is being pumped in. So in that regard, you're not tied to one specific supplier. You can buy an inverter from company A and batteries from company B. You're very flexible in that regard, which provides you a lot of resilience in terms of your supply chain and being able to manufacture these at scale and distribute them. You're also able to upgrade these systems piecewise as the technology improves. So batteries are one thing that will definitely need to be replaced over time, because even if you're using lithium batteries, those have a cycle life of about 10 years at most. So when those 10 years come and go, you'll be able to upgrade the batteries with the newest, latest, and greatest thing without having to replace the entire system. Another benefit of this commercial off-the-shelf technology is that it's designed to work with existing infrastructure, like the breaker box at whatever facility you want to power. It's easy to plug and play, isolate whatever building from the rest of the grid, hook it up to your box, and now you have power at your building. So between the benefits of the commercial off-the-shelf technology and the containerized system, you're able to have a very flexible way of getting power wherever you need it, even in the worst environments. These, well, maybe not the worst. These might not be suitable for the middle of Afghanistan, but they're certainly suitable for domestic instances where you might be responding to disaster relief, earthquakes, hurricanes, and such, or supplying power to infrastructure on a base that's that would be relying on the local electric grid that's been knocked down due to a cyber attack or something of that sort. Anywhere where you're not, in the middle of nowhere in the, in the middle of the desert, you should be able to, provide reliable power with these systems. Next slide, please. So one thing that we've worked on here at the Naval Postgraduate School that we're looking to expand in the future is a microgrid lab using this technology for students to conduct their experiments with. Because the technology used in this system is agnostic to whatever's plugged into it, we're able to hook up any type of technology the students want to experiment with via, or such as new types of solar generation, see how effective wind turbines are at different locations. We're able to test different means of storage and data collection. This is really just a playground for microgrid experimentation, and we're hoping to see more of that in the future. And with that, I'll open it up to any questions. Dan, you're on mute.
Thank you, Brandon. Appreciate that very much. And if people want to get in touch with Brandon, can you just tell us your email?
My email is Bravo Lambda November Alpha Yankee Lima Oscar Romeo at novemberpapasierra.edu.
Good, thank you. BL Naylor at NPS. Thank you very much. Appreciate it. Can you? Our next speaker is Daniel Eisenberg. Daniel is a research assistant professor of operations research at the Naval Postgraduate School in Monterey, California, and he's the deputy director of the NPS Center for Infrastructure Defense. His research focuses on the design, operation, and adaptation of resilient infrastructure systems with emphasis on applying resilience engineering theory to improve system design and emergency operations. He currently leads projects on the design and management of resilient island and military installation infrastructure systems. Dan?
How's it going? Thank you for having me. This is a really exciting opportunity. As Dr. Nussbaum just alluded to, my presentation will be essentially talking about infrastructure resilience on islands and installations with an emphasis on energy infrastructure. I'm going to start this presentation largely with an overview of how we view island and installation infrastructure systems and how we model them, and then some recent work that we've been doing to try and relate infrastructure resilience and modeling to missions and mission assurance, because that's what's most important for Department of Defense installations in the Navy or other services. So as Dan mentioned, I'm the Deputy Director for the Center for Infrastructure Defense. Everything I present to you today is easily accessible and available on our website, so I highly recommend you go check out nps.edu/CID. I work very closely with another professor in operations research, Dr. David Alderson, who's our director. And all the work that we do at the CID is associated with infrastructure resilience via vulnerability assessment with modeling and trying to protect infrastructure systems to various disasters, whether it's a natural disaster like a hurricane or some kind of terrorist threat like an adversarial attack. And I think it's worth mentioning that this session is being run by the Energy Academic Group, and we work very closely with Energy Academic Group as well as other faculty around NPS campus. So CID and EAG are kind of connections across many disciplines at the Naval Postgraduate School and outside of the university. In particular, we work very closely with lots of faculty in operations research, but also other faculty in computer science, like Justin Rohrher, as well as closely with several faculty associates and faculty associated with the Energy Academic Group, specifically Alan Howard, Tamina Karamova, and Jacob Weigel. So part of the reason I'm giving this presentation is because of the strong collaboration we have across NPS faculty and campus, and that this is really the product of us working together and working with local stakeholders in civilian systems and military systems to try and make infrastructure more resilient. So just a overview of the way that we like to think about infrastructure modeling resilience on island and installation systems. I want to emphasize that we view infrastructure through an operational lens. So we have strategic, operational, tactical levels of analysis and assessment we could think about. When we're doing work at CID, we're thinking in an operational way. The way that we'd like to talk about that is that infrastructure assets work together as systems to provide a function. That function enables capability, and capability supports mission. That mission could be either like an actual mission being performed by an installation, like missile defense, sorties, intel collection, or it could be like a civilian mission in terms of public safety, security, and economic development. So, but the thing that we want to emphasize is we don't necessarily care about a specific generator, we care about electricity. And so all the work that we're doing is trying to understand how different assets connect together to provide the function that electricity is supporting and the mission that electricity supports for either civilian or military systems. And in doing so, we try and protect the systems themselves rather than focus on a particular asset or technology. And so all of our work focuses on this relationship between building up assets into systems and how they support some form of mission. And just to give you an idea of the kind of work that I lead at the Center for Infrastructure Defense, we have military installations on the top. So that's a conceptual diagram of a base in the United States. One of our installations kind of for many services. This is originally based on an Air Force installation, but a lot of them have the same structure where you have some civilian power grid coming in, and then it has some local grid within the base that's serving many facilities, some of them critical with backup generators and uninterruptible power supplies. You'll look at the bottom half of this image, that's the island of St. Thomas and St. John from the United States Virgin Islands territory out in the Caribbean. And you'll notice in this system also has its own small power grid that's serving these two islands that's actually connected underwater. And the way in which we go about assessment actually applies in both these contexts almost identically because they all have the same kind of vulnerabilities and structure. So we have a single substation serving the entire base, and within the base you have like a contained unit of critical facilities and operations you're trying to support. On the islands, you have a single major generation plant that's serving the entire community. And in a similar way, you have power flow in one direction. And if anything were to happen across the system, it could affect the communities or the critical facilities for government or public safety, education, healthcare across these islands. And so the methods and techniques we apply at the installation scale apply to the island scale, and in the island scale apply to the installation scale. Focusing now on military installations, what we're trying to really understand is the impact of some kind of failure in the power grid or other infrastructure systems. This could be transportation, water, fuels, or otherwise, and how it affects operations within that installation. Essentially, your uninterruptible power supplies and backup generators should kick on, and you should make sure that your critical missions can still have electricity that they need. But when that failure happens, you tend to have these interdependent effects. So the resilience of your energy system depends on, transportation, so you can access, repair that substation. You need to move fuel and have controls, telecom, to operate these backup generators, especially if you're operating them beyond their normal operational life of maybe 24, 48, or 72 hours. The loads at these facilities need to change. So if they're serving like pumps for water distribution or other kinds of critical assets on a base, you need to adjust those loads to have these backup generators work effectively. And sometimes you need to actually move electricity within the base to other facilities from the generation that you have. So there's all these interdependencies that occur. And when we focus on energy resilience, we're not just looking at a single system, the power grid itself or the fuel network itself. We're trying to look at the interdependent effects and vulnerabilities across them. The way in which we go about doing that is by developing and using tools from operations research, specifically network flow optimization is kind of like the focus of our methods, but we include stochastics and statistics in terms of stochastic optimization and other kinds of reliability assessments. And we can essentially measure the operations and function of our critical systems like electricity, water, transportation, telecom, fuels, using these methods and models to get a realistic understanding of how power will flow, how fuel will move across these pipelines, and understand if a pipe were to break, if a pump were to go down, if a generator fails, how that actually affects access to that critical asset, that service, and how the missions and the operations on the base might respond. And I think it's important to emphasize that our techniques scale to essentially any size of a system that we care about. So, the island of St. Thomas and St. John is kind of like a medium to large installation. We could do this at a much smaller scale or even a larger scale. And we've developed many tools for doing this form of assessment. So on the left, you'll see the island of St. Croix, which is also in the US Virgin Islands. We have on the top a power grid model that's essentially measuring how many customers lose electricity when certain components fail. In the middle, we have a water distribution model that's telling us which communities might lose access to water when pumps go down. And on the bottom, we have a model for transportation that's telling us which roads are going to be the most congested when everyone's trying to get critical disaster supplies to prepare for after the effects of a hurricane. And these three models for power, water, and transportation, we can apply to our installations that are also in remote and isolated locations like Marine Corps Base Hawaii, which is in Kaneohe Bay community. There's the base and the community that's essentially isolated on the island of Oahu. A lot of the work we're doing right now is taking these models we've developed for civilian systems and applying them to military systems. And the way that we're making that link is not just through the technical approach for modeling power, water, transportation, telecom, fuels, but also trying to link it to DoD-specific measures of performance and understanding of mission. And in particular, when it comes to how infrastructure supports missions on our installations, there's two key performance indices: facility condition index, which is essentially a measure of quality of our infrastructure. Is it dilapidated or is it brand new? Is it going to work for our mission's purposes? The second one is the one we're really focusing on, which is mission dependency index, which is a measure of capability, which is essentially saying how well does this infrastructure support mission? What are the critical missions at these facilities? Which ones are interruptible and which ones need power all the time? And these relate very closely to a lot of DoD requirements for installation resilience. So across all services, we have requirements or plans for having like 7 days of energy given a blackout on a civilian grid, or if you're like Army, 2 weeks of energy and water. Air Force is 7 days. Marine Corps has talked about 2 weeks of multiple systems, no specific requirement yet. But all the work that we're doing is towards this robustness of our installation infrastructure systems to make sure that our missions that require these critical services to operate can remain operational given disruptions to these larger infrastructure systems that are supporting them. And getting more detailed on mission dependency index, there's essentially three key factors that are being considered when you're trying to determine like how well, you know, this power grid might be supporting mission. The first one is interruptibility, which is essentially saying how, if this facility were to lose power, would that interrupt critical missions on this installation? The second two are relocatability and replaceability, essentially saying, is it easy to move this mission to another facility, or is it very, very difficult? Or is it easy to replace the equipment or the facilities that this mission requires with something else? And that essentially relates the movement of power to our facilities at our installation and how power needs to move around our installation to make sure that the critical missions that are being supported by those facilities are able to continue operations given disruptions to either the power grid or other kinds of services. And a lot of the ways in which this has been calculated across all services is essentially through expert elicitation. What we're trying to do right now is take the operations research tools that model and provide real measures of service provision and relate them to these MDI values and scores to better understand how infrastructure supports mission and how we would view its vulnerability from that perspective and how we would protect it to ensure our missions remain operational given disruptions. And so we're taking a new way to try and measure mission dependency across all of these systems. So just a brief overview of results in the last couple of minutes for some recent work that we're doing. We have 3 students right now working on this topic. The first one's trying to understand interdependent effects and vulnerabilities across multiple systems. On the left, you'll see a network representation of a fuel distribution system. On the right, you'll see a network representation of a power grid. They're interdependent with each other. The power grid needs fuel to operate its generators. The fuel network needs electric power to operate its pumps. And we're doing all this modeling using open source available tools, so we can run it on civilian systems or military systems as long as we have the data and information. And what Matthias Kutz, who's a German army officer, is doing is really trying to understand if there's failures in an interdependent system like the power grid, how will that affect these fuel operations and vice versa. And so we really want to understand these interdependent failure effects, because the vulnerability of our fuel system might be greater if we're just looking at the power system vulnerability, or potentially failures in the fuel system could cause cascades that then cause issues in fuel delivery across our installations. So this is very energy focused and very focused on this interdependent vulnerability, and we're trying to apply this at an installation scale. The second study that's going on is being run by Lieutenant Commander Fish, who's a U.S. Navy officer, Supply Corps officer. And what we're trying to do is take this mission dependency index values and relate them to interdiction methods that have been developed for a long time within the NPS department to understand the worst case vulnerabilities of these systems and how that affects missions. So these IRR, interruptibility, relocatability, replaceability uncertainties. We use stochastic optimization, and we're also thinking of mission dynamics and time simulation. What this ends up doing is you take your fuel network, you disrupt it, we remove 2 of these pipelines, every combination of 2 pipelines, you end up with all of these blue dots that represent different system states, where generally interdiction methods are trying to make a network operating cost as high as possible for the fuel operator. Well, now we're trying to measure the actual effects on mission as well by having mission dependency index scores and interdependencies across the missions themselves. What you'll notice is when you do this kind of assessment, you end up with a view of vulnerability that's worse for the fuel operator, which might be different from your view of vulnerability that's worse for the installation mission. And what we're working on right now is trying to balance these multiple objectives. How do you deal with trying to disrupt the delivery of fuel the worst, as well as trying to disrupt the mission the worst? And how does that tell us about the vulnerability of our infrastructure if we want to then go protect these pipelines and say we're going to harden these systems because they're the most critical for ensuring missions and ensuring operations? And then the last study is by Lieutenant Pulliam, who's also U.S. Navy. He's a Civil Engineering Corps officer. So he's got his PE in civil engineering. He's developing a queuing model for fuel operations at a port. So the 2 models before are talking about, if you look at the bottom, this network fuel approach of actually moving fuel across an installation. Daniel Pulliam is looking at how we actually get that fuel to the ships and how well we can serve ships if we have storage tanks and berths. And what he's finding is how we can actually model the real mission and how it changes over time given disruptions to our infrastructure. And so we have a percentage of fuel ships that we want to fuel per day, and under normal operations, giving a couple of tanks, we actually are able to serve well over 90% of all the ships that arrive every single day with high reliability. When you have some form of missile threat or disruption, you have to have many, many more storage tanks as backups just to make sure that you can serve that same number of ships that might be coming to support the warfighter and project power. And this information is now linking to that network operations view that we had in the previous studies to the actual operations that are going on at a port for resupply, refueling operations and missions. And this is leading to actual recommendations to the NAVFAC, Civil Engineering Corps, for how they would invest in protecting fuel operations and missions, given the information of the vulnerabilities and the actual operations at our installations. And so the current efforts that we're working on for energy resilience is
And
linking
Dan,
all of this work together.
We have about
Yeah.
1 minute left.
That's perfect. This is my last slide. So the current efforts we have are linking all of these studies together to better understand interdependent effects across energy systems, how they relate to our understanding of mission dependencies across our installations, and then how that relates to the actual operations and changes in dynamics over time as ships need refueling and how they arrive and leave, and how the ports actually support the warfighter and projection of power. And so these are the work that we're doing at the Center for Infrastructure Defense. I hope you found it interesting, and please feel free to reach out to me if any of this is useful or helpful for your own work. And I just wanted to acknowledge our funding source, which is the Office of Secretary of Defense Strategic Environment Research and Development Program, CERDIP, which is funding us to understand these interdependencies and vulnerabilities on our installations and make better models and tools for protecting them. Thanks.